about anything? Be getting a new homework shortly. So, been getting a few homework 2s. Let's keep them coming. Okay? Yes?
Our friend broke his arm. It's like a scientist get well sweetheart. That's his student in the class.
Sure, sure. Who?
Alex Moss.
Oh, really?
Yeah. He was still learning.
Oh, neat. Okay, yeah, bring it up during the break or after. I'll definitely sign it, yeah. Oh, yeah, the solutions, I keep forgetting to put those up. They're ready to go. I was going to put them up this weekend. I'll put them up. And the grader has homework 1, and so when he's done with those, I'll give it back to you. Any other questions? Okay, well, now today the first job is to undo the mystification of last time. I remember at the very end of class last time I started on some what I consider elementary kind of warm-up examples of this Monte Carlo stuff, and everyone just looked completely mystified. Well, not everyone. Everyone but Matt. No, just kidding. Look completely mystified. So what I want to do is I want to sort of reset that a little bit. So essentially what we're going to do now, we're going to talk about putting Markov chains to work for us. We've learned all about Markov chains, and so the sort of the general theme of what's going on for the next few lectures and into the discussion of the theory of genetic algorithms is essentially putting Markov chains to work. And part of this is going to be history, the history of all this kind of random searching kind of stuff that goes on, and genetic algorithms is a modern example of that. So what I want to do first is I want to talk about the earliest examples of sort of algorithms that exploit randomness to do their jobs. They arose in the 1940s at Los Alamos. Some of the scientists there were kind of bored because they were done with the atomic bomb, and they needed something else to do, right? There was no more war. So Ulam and Metropolis and all those kind of people who were at Los Alamos started thinking of these things, and the inspiration was the availability of computers, computing machines, not computers in the sense of people, as they were talked about at Los Alamos, but actual machines that could perform computations very rapidly, at least very rapidly for the 1940s. And I just want to emphasize that Stanislav Ulam was a very important guy at the center of all this. And Ulam is credited with naming the first example of this sort of thing, which goes under the very general umbrella title of Monte Carlo methods. So first, what we're going to do is talk about, in a very general way, sort of a general sort of circle of ideas encompassed by, notice I'm putting more words on the board than usual because that more words means less mystification in general, at least in my experience. Okay? Encompassed by the name Monte Carlo methods. And really, the thought you want to keep in the back of your mind is all this stuff is essentially a version of putting Markov chains to work. Okay, that's what it's going to end up being. Okay, so what about these Monte Carlo methods? The key mathematical result that sort of hovers in the background behind all this so the key mathematical result underpinning everything, and it also underpins something we've seen already, the ergodic theorem for Markov chains. And we're going to return to that later on today. But just incidentally, in order to prove the ergodic theorem for Markov chains, you have to prove this key mathematical result, and it's called the strong law of large numbers. And this is something, if you look in a book that actually proves it, you'll see that the proof, there are various ways of proving it. Some of them rely on something called ergodic theory, which was developed in the early 20th century by Birkhoff and others. And that's a much more general theory. It relies on measure theory and all that. And other proofs use sort of just classical probabilistic reasoning, but they involve countless technical lemmas and whatever else. And so they're really not a lot of fun to read. Okay. And so I'm just going to state this. And by the way, we usually call it by its initials, SLLN. Okay, so what does this say? This says that if Z1, Z2, Z3, ... is a sequence of independent and identically distributed and the abbreviation for that is IID. So I'm going to use that a lot as well. Random variables. With a common, and I'm putting common in parentheses because of necessity, because they are identically distributed, they all have the same expected value. So common expected value, let's call it Z bar. And I'm assuming that exists as finite expected value. Then the following is true. If I form the sum divided by n, sum from m equals 1 to n of Zm, so that's the average of those random variables over the first n. As n goes to infinity, this converges with probability 1 to Z bar. Okay? So, for example, suppose you have a fair coin, right? So, fair coin is a two-sided coin, half probability heads, half probability tails. If you flip it and you record how many heads, or head, every time a head comes up, every time a tail comes up, you record that. And you think of the head as having value 1, say, and the tail as having value 0, and you add up all those 1s and 0s and divide by how many you've done so far, then as the number of flips goes to infinity, that's going to converge to 1/2, because that's the expected value of that random variable, a variable that assigns 1 to heads and 0 to tails. So that's just one example. And in fact, for a random variable like a coin flip, a so-called Bernoulli random variable, you can prove the strong law of large numbers without the kind of general horrible lemmas that you need to prove it in general. Rishi, question? The central limit theorem is about the probability distribution of these things, if you scale it properly, is asymptotically Gaussian. Okay? It's related to that. Yeah. The same kind of horrible lemmas and whatever are behind the central limit theorem as are behind the strong law of large numbers. Drew?
Would it be correct to say that the strong law of large numbers is sort of like the basis or the fundamental one, and then the central limit theorem grows out of that? Or
They're kind of side by side. They intersect. You can't prove the central limit theorem from the strong law of large numbers, nor can you prove the strong law of large numbers from the central limit theorem. But they are branches of the same tree, or trees in the same forest, or some horrible analogy, whatever. Okay? Now, there are more general versions of this, like I said. But anyway, that is a fundamental result. And if you look at the handout, if you look at say, the proof of the probability 1 convergence of the fraction of the time you spend in state J, blah, 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 in the handout on Markov chains, you'll see exactly where the strong law of large numbers comes in as part of that proof. Okay. So that's an important rule of probability. Now, given the strong law of large numbers, and given the fact that these Los Alamos guys noted that computers are pretty good at generating random numbers distributed uniformly on the interval 0 to 1. Okay, given that fact, the strong law of large numbers inspires a variety of ways of using this fact about computers to do computations that you sort of can't do in closed form. And that's what I want to segue into from now. Now, you know, for example, like in MATLAB, I guess there's this rand function, right? Generates a random number between 0 and 1. And the computers do this in a number of ways. They do it, sometimes they're true pseudo-random numbers where they iterate a dynamical system and to stop it suddenly. And other times they read noise values, you know, whatever. But computers are pretty good at generating random numbers distributed uniformly on 0, 1. Now, given this fact, like, suppose you had, say, a fair coin. You wanted to simulate the operation of a fair coin. And all you were able to do was use the fact that computers are pretty good at generating random numbers distributed uniformly on 0, 1. What would you do if you want to simulate the outcome of a bunch of coin flips? 0 to 0.5. Yeah, you would, what you would do, you generate a sequence of random numbers in 0, 1, and you would regard any outcome in 0 to 1/2, or 0 to 0.5, as you said, as being, say, a head, and the other one as being a tail, that kind of thing. So there's all kinds of ways of using this to generate Bernoulli, and you can generate binomial, multinomial, all that, because those all build on the Bernoulli. But anyway, I'm not going to talk about that for now. The point is, computers are pretty good at generating numbers uniformly distributed on 0, 1. Okay, so here's an application that puts these two things together. So putting strong law of large numbers together with this fact leads to this idea of Monte Carlo integration. And I want to just talk about a couple of very simple examples. And the first one was the one I talked about at the end of class last time. Okay, and the one that seemed to mystify everybody, so I want to do it carefully now. So Monte Carlo integration. And this is the first thing that these guys did using randomness and computers together. So here's the problem. You have some function, g, say, a real valued function with domain 0, 1. And this notation, again, this is the 3250 notation. Okay, I'm not criticizing you if you didn't take 3250, but whatever. And you want to compute, you want to find integral from 0 to 1 g of x dx. Now, that's pretty simple if g is like, you know, e to the 17t, or sine of 3 pi over 2t, or sine 3 pi over 2x, or whatever. But it's not easy when g is complicated, right? So what we're thinking here is that this is too hard to compute in closed form. You can't use any range of Thomas and Finney trig substitutions or whatever to do it. Okay, so how do you think how we're going to do this? How are we going to do this? Here's the Monte Carlo solution to this. To this problem. You use your computer to generate a sequence of samples uniformly distributed on 0, 1. So use your computer to generate the sequence, say x1, x2, x3, dot, 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 of samples, and I'll put that in parentheses, IID uniform on 0, 1 random variables. That's the first thing you do. So you're going to have this long bunch of uniform samples. And depending on what numbers actually come out when you have the computer do this, that's going to depend, probabilistically on stuff. But anyway, okay, so just keep that in mind. Now what we're going to do is we're going to define random variables say z1 equals g of x1, z2 equals g of x2, and so on. So essentially, we have this function g. Even though we can't compute its integral in closed form, we assume that if we're given a number, it's fairly easy to plug into g and figure out what the value of g at that number is. So this assumes that given x, you can easily compute just the value g of x somehow. It's quite easy to find functions that are hard to integrate in closed form but are easy to evaluate. Okay. Now, notice that because these x's, these uniform things, if you think of them as a sample record of IID uniform random variables, because they are IID, the z's are IID as well. So here's some observations about the z's. First of all, z1, z2, up through whatever are IID. They're independent and identically distributed because each one is just a static, memoryless function of an independent, identically distributed random variable. That's the first thing to note. The second thing to note, what is the necessarily common mean, common expected value of the z's? So the common expected value of the z's, the zm's, is given by the following formula. Integral from 0 to 1 of g of x dx. Now this is where people's eyes glazed over. Now I'm trying to figure out why. Okay? If you have a uniform random variable and you take a function of it, like it squared or it cubed or e to the it, and you want to compute the expected value of that random variable, what you do is you take that formula and you integrate it times the probability density of the x that you plugged in. Okay? The probability density of the x you're using here is uniform on 0, 1. So it's just 1 between 0 and 1 and 0 elsewhere. So if you want to formalize this, I'll put quotes around this. This is equal to e of g of x, which is just equal to the integral of g of x p x of x dx. So that's sort of like ECE 3100 notation, I think. Whatever. Got that? Taylor? Mystified? No? Not picking on you. You're not the only one. Now, I hereby, I've broken a promise to you. Day 1 of the class, I said, what do you need for this course? You need discrete probability. There's no densities. This is the one time in the semester when every now and then I refer to a density. Forgive me. Okay? It's unapologetic that I'm doing this, but that's why I give you the forgive order in imperative style rather than please forgive me or anything like that. Okay, anyway, enough of that. Yes?
So the x of x is that discrete or is that continuous?
This is continuous. The x's are uniform random variables on 0 to 1. So they are continuous valued random variables. And the probability that x lies in any given interval is just the length of that interval. That's what uniform means. Does everyone know, when I say a uniform 0, 1 random variable, does everyone know what that means? Yes, right? Okay. All right. So anyway, that's the common mean of the z's. So what is it? What do we do? We've used the computer to generate samples of IID sequence uniformly distributed on 0, 1. We plug those samples into the function g, and we get the z values. The z's are an IID sequence with this common expected value, and therefore, by the strong law of large numbers, if we compute 1 over n sum from m equals 1 to n of zm, and that's supposed to look just like that one over there, that's equal to 1 over n sum from m equals 1 to n of g of xm. That converges as n goes to infinity with probability 1 to z bar, which is integral from 0 to 1 g of x dx, which is what we wanted to compute. That's what we wanted to find, and this is how we find it, at least approximately. We generate a sequence of random samples uniformly distributed on the unit interval. We plug them into the function g, and we average those samples over time. We let the time go, and eventually this thing is going to start converging to g of x dx integrated. Now, what is this business about with probability 1? And remember, put samples of in parentheses here. The idea here is that you're using your computer to generate an actual sequence of numbers. The computer doesn't spit out random variables, it spits out numbers. But with probability 1, the numbers the computer spits out are going to be such that when you plug them into the g and you average them from 1 to n and let n grow, it converges to z bar. That's the point. Now, there's a little bonus here, by the way. Once you've used your computers to generate a good sequence like that, you can use that sequence again and again and again on different g's, right, to compute their integrals. So I could sell you a CD that has a sequence of uniform samples drawn from 0 to 1, and you could use that on different g's. Now, one problem is that, or I could give it to you. That would be more academic of me, less businesslike. But the point is that it turns out that some particular samples might be in this probability 1 set for one g, but not in the probability 1 set for another g. So you might, I don't want to get into that fine point. So that's the most elementary thing, the most elementary example of using random numbers to do something. And if you don't get this, then, well, no, let's put it this way. Getting this is important for us to move on, okay? Try to think in half full. So let's make sure we're on the same board panel.
You do this because you have to get the integral, it's too hard to do it.
Yeah. Suppose g of x is some horrible combination of exponentials and sines and Gaussians and Bessel functions and you name it. Some hideous Bessel functions. Paul, question? They might come out that way, but, you could, and with high probability those would work just the same way, but the problem is that if you sell a systematic set of uniformly spaced things, then I can easily find a g for which that sequence, that particular sequence, is in its non-converging set, its probability 0 non-converging. Like any g that vanished at all those points, but had a non-zero mean, right? So if you want it to work for most g's, then you really need to generate them randomly.
you encounter, like, for any randomly generated, there's at least one G that vanishes at all those points.
Exactly, correct. That's what I was saying a minute ago, that a sort of generic in this sense sequence of x values for one G is not going to work for all G's. And you gave a one-line proof that that's true. Like, you could pick any function G that is 0 at all those points and doesn't have a 0 mean.
I suppose if n goes to infinity, then like the randomly thing becomes the linearly spaced one. You just have every value.
Well, remember, you're only generating a countable set of numbers, and the interval 0, 1 is uncountable. So you're missing a set of full measure, so to speak. So these are all good questions, but you know, they do indicate to me that we're pretty much on the same board panel with this, I think. Okay? Okay, next problem. And this is actually sort of a special case of this one, except it's one dimension higher. So here's another problem. You have some awkwardly shaped two-dimensional region. Call it D. So let D be some awkwardly shaped two-dimensional region. And I don't want it to be too horribly awkward. It could be bounded by some curves, but the curves are nasty, right? So perhaps bounded by curves whose formulas we know, but they're complicated. So D might look like this. Say, something like that. Okay? That's an example of an awkwardly shaped two-dimensional region. And all those curves have formulas, whatever. Now, what I'm going to assume here is that it's fairly easy if someone on Ho Plaza comes up to you on Ho Plaza and hands you and says, here's an x, here's a point, here's a value of a point. Is it in D or not in D? And I'm going to assume that's fairly easy to figure out. So assume, given some point, and think of this as being in the xy plane, if you wish, something like that. Say x1, x2. Some x1, x2 pair, call it x. You can easily figure out whether x is in D or x is not in D. And this is the same thing as assumes given x can easily compute g of x in the earlier thing, in the following sense. So in other words, we can, quote unquote, easily compute the characteristic function of D. And remember this from last time, the characteristic function is 1 if x is in D, and 0 if x is not in D. And this is also known as the indicator function. And that letter is supposed to be a chi, which sounds like hi, which means life in Hebrew, and all that. We went through all that last time, right? For those of you who weren't here. All right, so you want to compute the area. And because the curves have complicated formulas, you can't do it using like 2D integrals like you did in Math 1920, right? So what do we do? What do you think we do? Paul? Yes. Exactly. It's exactly what we do to solve the problem. Okay. So here's the solution. This is the Monte Carlo solution to this problem. you surround D with a, just let's make it a square, okay, with a square, and let's call it, I used to call it V, but then it occurred to me that it's better to call it U for Ulam, whatever, okay? So surround D with a square U, okay, and from which you can draw uniform samples. So it's easy to draw uniform, or samples that are distributed uniformly, IID, uniform on capital U, samples. How would one do that? How would one draw? Let's draw the picture of the box here. So this is U. How would you draw points uniformly on a square? Yes?
Two patterns. That's separate sampling.
Exactly. You just draw an x2 sample and an x1 sample and put them together. Then draw another x2 sample, another x1 sample, put them together. Okay? So just do this coordinate-wise. Okay? So it's easy to draw. And what we're going to do essentially is, as Paul said, we're going to compute the fraction, the fraction of points that end up in D from this sample sequence. And that, suitably normalized by the area of U, is going to be the area of D. And I'll show you that in terms of the strong law of large numbers in a moment. So it turns out that what is going to be true? The area of D is equal to the fraction, let's put it this way, the limiting fraction of samples that lie in D times the area of U, which is easy to figure out just by taking the product of the two sides of the square. Yes?
So why are we using square, not say rectangle?
No reason.
It can be any arbitrary size square or...
Yes. But we'll see there are reasons for choosing it certain ways and not other ways. But yeah, Drew.
So it's sort of intuitive. Like when you prove that you have IID uniform random variables, when you pair them up in coordinates, there's still random IID over a chain. Like,
Yeah, you can prove that. Yeah.
Professor, sorry.
Yes.
When you're populating the samples in the square, when you say IID uniform on U, is that going to be like, does that matter on the sample, like the space between your x, like the x1s and the x2? Like basically if I say you can take it at every point 1 or every point 0, 1, every point 0, 0, 1, is it going to be like distributed, like everything's going to have, you just drop?
They're not going to be distributed in a systematic way over the region U. They're just like in the other, we were talking a minute ago when we were talking about the interval, we talked about reasons why you wouldn't want to choose like every 10,000th.
Okay.
Okay? You want to flip coin, you want to choose them randomly.
Okay.
So they're kind of all over you,
So
but not in any systematic way.
Instead of dropping like here, 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 like you know
Right.
what I'm saying? Like
Yeah.
you're just basically taking a pail of numbers and just chucking it there and just hoping it's everywhere, right?
Well, you could think of it that way, but what the computer's doing is one at a time. It's picking a random number on this axis, a random number on this axis, and then plunking a point down. Then does it again, then does it again, then does it again. So it doesn't take a whole bucket at once. It just fills the bucket one at a time. We're using lots of analogies today.
It's not really saying, okay, I'm going in a particular step.
No. They're not systematically distributed. And for those of you watching at home, they're not systematically distributed, okay, over you. Okay, I said it turns out that's, any other questions before I prove that's the case using SLLN? Okay, so here's the proof that this is true. So to see this, first of all, what is the uniform density on the square U takes the following form. And let's just call it P of x, just for the heck of it. It's equal to 1 over the area of U if x is in U, and 0 if x is not in U. That's what the uniform density on U looks like. Okay? Now what I'm going to do is I'm going to define. So when I choose these uniform on U samples, they're according to this probability distribution. Okay, so the uniform samples are distributed according to this P. Okay, now I want to define a G and a Z associated with that. Okay, so say these uniform samples are x1, x2, x3, and so on, and I don't want to confuse these subscripts with the little subscripts that delineate the axes. These are all pairs, so each is some point, say x in U, or a random variable distributed according to that point, whatever. I'm blurring that distinction. Okay, now I want to let g of x, define g by means of the following formula. And I have to get the factor right. Okay, g of x is equal to the area of U times characteristic function sub d of x. So it's equal to area of U when x is in D and 0 when x is not in D. Now note that computing g of x is the same as computing chi d of x, which we already said we could do quote-unquote easily. Okay? And I want to define the z sequence just by plugging the x's into the g's. So z1 equals g of x1, z2 equals g of x2, and so on. What is the common expected value of these IIDZs? So these z's are IID. Their common expected value is going to be what? It's going to be z bar is equal to the integral of g of x times p of x dx, where the p is that uniform distribution over there. And that's just going to be the integral over u of area of u times chi d of x, that's g of x, times p of x, which is 1 over area of u, times 1 dx. And that's just going to be, the areas of u's cancel, the integral over d of chi d of x dx, which is just going to be the area of D, the thing we wanted to compute to begin with. If you integrate the characteristic function of a region over that region, you get the area of that region. And by the strong law of large numbers, if I just compute the sum of these g's divided by n, up through n, and divided by n, and let n grow large, with probability 1, that's going to converge to z bar. So by the SLLN, this thing here, 1 over n, sum from m equals 1 to n of zm, which is 1 over n, sum from m equals 1 to n of g of xm, converges as n goes to infinity with probability 1 to z bar, which is the area of D. And you can actually, you can see when you look at it carefully that this is just the limiting fraction of things that end up in D times the area of U, which was our intuitive way of looking at this. Okay? So this is like 2D Monte Carlo integration in some sense, with a very particular kind of G. Yes?
Does it hold true for any random function G, like without the area of U?
Yes, you could, if you wanted to integrate any G over this region, yeah. But I just wanted to look at a very specific case of computing the area of a region just for the heck of it. Part of the reason I want to look at that is because it's easy to think up regions that are bounded by complicated curves where it's easy to figure out whether a point is in or out. Depending, if someone hands you a point, you can say, is it below this curve or above this curve? Is it to the left of this curve or to the right of this curve? You just go and you do this finite number of tests. But the curves could be so complicated that you could never possibly do an analytical integration between them. Okay, so far so good? These are two elementary examples of Monte Carlo techniques, using randomness to compute things that are hard to do analytically. Okay. Now, we haven't talked at all about how fast does this convergence take place. Rishi, are you raising your hand or just doing this? Okay. All right. Trying to be attentive to, hand raising and mystification, looking, and oh, and by the way, a shout out to Alex Moss. If you're watching this, I'm sorry you broke your wrist or whatever, but at least you were snowboarding, right? And not doing something stupid. Well, no, I mean, you could be you could be snowboarding really well and daringly and all that, and break your wrist, or you could be like I would be, like chicken, kind of like trying to, I don't know.
That second one.
What's that?
Stupid anyway.
It was stupid. Okay. Yeah, I mean the recently, the wrist cast is a very common like skateboard, snowboard kind of injury. You see those around a lot. All right. So anyway, here's something we haven't looked at yet. So here's a question. How fast does 1 over n sum from m equals 1 to n of zm converge to z bar in the strong law of large numbers? Because this is, when we look at this question, this is going to inspire all the different modifications of this Monte Carlo technique that bring Markov chains into play. Well, what do you mean by how fast does that converge? So here's the answer. I'll tell you the answer first. This is how people talk about it. They say it converges like 1 over square root of n. Not very fast. That's the colloquial way of saying how fast it converges. And it turns out the 1 over square root of n is something we can't do anything about, but the like is something we can do something about. Okay. So what does this mean? So meaning, question mark. let's compute the variance of that thing about its mean. Note, for any n, the expected value of that nth thing, m equals 1 to n, of Zm is equal to what? What is that equal to? Remember, Z1 through Zn are IID.
So the expected values of the individual.
And what is that? Remember, they're IID with a common expected value Z bar, right?
Yeah.
Yeah, so each of these, this is equal to 1 over n times n Z bar, okay? Or Z bar. In other words, the expected value of the nth sum that is going to end up converging with probability 1 to Z bar is Z bar all along. Okay. What is the variance of that thing about Z bar? So the variance of 1 over n sum from m equals 1 to n of Zm, what's that equal to? Variance of a random variable is the expected value of random variable minus its mean quantity squared, right? So this is the expected value of 1 over n sum from m equals 1 to n of Zm minus Z bar quantity squared. And you could separate the Z bar into 1 over n times the sum of n Z bars. This comes out to be E of 1 over n sum from m equals 1 to n of Zm minus Z bar, all that squared. And because the z's are independent, the cross terms go away when I take the expected value. So this is equal to, by independence, it's equal to 1 over n squared times the sum from m equals 1 to n of E of Zm minus Z bar, the quantity squared. Okay. And these are all the same because of IID, because of the ID part of IID. So these are all the same. By ID, by independently distributed. Let's call their common value variance of Z. Just call it that, just for the heck of it. And you have n of those, and you have a 1 over n squared, and therefore you have 1 over n times var of Z, the common variance of all the z's. Okay? So why do people say it converges like 1 over square root of n? Yeah. Yeah, the standard dev is 1 over square root of n times the standard dev of z. So thus, the standard dev of 1 over n sum from m equals 1 to n of Zm is 1 over square root of n times the standard dev of z, sigma of z. And that's why people say it converges like 1 over n. Or, sorry, 1 over square root of n. Now, as I said a moment ago, the 1 over square root of n is something you cannot do anything about. But the like part is something you can do something about. So thus, people say it converges like, and the like is the variance or the sigma of z, square root of n. That's the denominator. Okay. So far, so good? All right. Anyway, what I want to do is I want to look at the variance of the the nth partial sums for these two examples we've looked at already. So let's revisit the two examples above, just to do a kind of a calculation on the variance of the thing. Right. So for the first example, remember what the first example was? It was computing integral of g of x dx. Let's take the 3-minute break now and do that, because I see some glazing over happening. He has a question that might be relevant too. Okay. Will, I can't hear him. Say it louder. This I want to call var z. Each term. There's n of those, and one of the n's cancels, and I get, okay, got it? Okay, so I want to revisit these two examples, and what I'm going to use is a common formula from probability. Okay, we're going to use this, that if I have some random variable y, the variance of y is equal to e of y squared minus e of y squared. That's easy to show. Okay, and that helps, it turns out. Okay, so we're going to use that formula. So first example, okay. Remember we were computing e of z, so the z was g of x, and the e of z was integral from 0 to 1 g of x dx. And what is e of z squared? That's the integral from 0 to 1 of g squared of x dx. And therefore, the variance of the estimate, the variance of z here, is equal to integral from 0 to 1 of g squared of x dx minus the integral from 0 to 1 of g of x dx squared. Okay. Now, depending on what g is, that could be big, it could be small, whatever. We're going to come back to this in a context of a specific example a little later on. So what was example 2? Example 2 was computing the area of the awkwardly shaped region, right? And in this case, our z was equal to area of u times chi d of x. And I'm compressing a lot here. I'm not, just so I don't go through the whole example, but if you took notes, or if you're watching the video at home and you look back at what we did there, you'll see this, why this is the case. And remember what E of z was? E of z was area of D. Z bar is what we called it before. And what is E of z squared? Well, let's figure out what z squared is. Z squared is the area of u quantity squared times chi d of x, the quantity squared. What is chi d of x, the quantity squared? Trick question. What if I take a characteristic function and I square it? What do I get? You get it right back. So this is the same as the area of u squared times chi d of x. Because chi d is always, any 0, 1 function, if you square it, you'll get the function back. Did you ever think about that? Any function that takes on only the values 0 and 1, if you square it. Any function that takes on only the values of 0 and 1 is chi d for some d. What is d? D is the set of all x for which it equals 1. There you go. All right, anyway, lots of good math stuff here. Okay, so what's E of z squared? E of z squared is the integral from 0 to 1 of area of u squared chi d of x times p of x dx. And remember, p of x is 1 over area of u times 1, or not 0 to 1, integral over u. Sorry. So this is, and so the 1 over square root of 1 over area of u, one of those factors cancels this, and you get the area of u times the integral of chi d over u, which is just the area of d. So that's what E of z squared is. Therefore, the variance of z is going to be the difference, this minus this squared. If I've done everything right, var of z is equal to area of u, area of d, minus the area of d, the quantity squared. Right? This is E of z squared, and this is E of z quantity squared. Now that may not look in its current form very informative, but let's factor out an area of u, area of d. From both terms, and I get 1 minus area of d divided by the area of u. I think. Okay. And you can do something further here, but I won't. What do you think, just intuitively? Intuitively. Well, let's do it anyway. Let's do this. This is the same as area of u, the quantity squared, times the following. Area of d over area of u times 1 minus area of d divided by area of u. The thing in the brackets, it looks like alpha times 1 minus alpha, right? What is your intuition, without doing any calculus, what value of alpha, what value of the ratio of area of d over area of u maxes that out? What's that? Yes. If area of d is very tiny relative to area of u, or if area of d is very close to area of u, if it's a tight fit, I'm missing a parenthesis here, then one of these terms is going to be almost 0, and one of them is going to be almost 1. But if area of d is about half of area of u, that's going to max it out. So this variance is maxed out when area of d divided by area of u is on the order of 1/2. Yeah, you sort of want it to be a tight fit. At least that's what I would do. Or a very loose fit, but then you're going to be taking lots and lots and lots of samples. I don't know. But the point is that, you know, there's a user choice in example 2. A user choice. The region U, right? Jason, you don't like that. Bad pun? What? Yeah, whatever. Use for ulam, remember? Use for ulam. All right, so there's a user choice here. The letter U is a user choice. Matt?
Wouldn't that imply, though, that if U is infinitely large, you would have no variance?
Yeah.
So then why would you have a box? I guess it's...
Yeah, the thing is what you're going to be dealing with there, if you make U too big, you're going to be dealing with numbers that are smaller than the floating point precision of whatever your calculation you're trying to do, that kind of thing.
Okay.
So there, you know, there's all kinds of compromises here, but the bottom line is there is a way to reduce the variance of this estimate, and that's to make U a fairly tight fit around D. Okay. All right. So those are putting this varicon thing, this how fast does it converge? It converges like. The like part is the variance, and the square root of n is something you can't do anything about. Now, why do we care about this? Well, I want to look at another example. So here's another example. So here's a third problem. We've talked about two so far. Here's a third problem. Suppose I'm given some probability density function on the unit interval. So I'm going to let P be some arbitrary density function on the unit interval 0 to 1. And you want to compute the expected value of some function f, and I'm going to write that as EP of f, for some function f from 0, 1 into the reals. What is EP of f? What does that mean? EP of f just means integral from 0 to 1, f of x, p of x dx. Computing the expected value of that quantity with respect to the probability distribution p. Now, p could be any shape you want. I'm going to show you two ways of doing this and try to sell you on why the second way is better. Okay, so here's method one. Method one, and I'm going to try to get you to tell me what method one is after I give you a little bit of notation. I want to define the function g from 0, 1 into the reals by g of x equals f of x, p of x, for x in 0, 1. Okay, now, can someone suggest a way of computing this guy, the EP of f, based on our discussion so far? And the G notation is supposed to give you the big hint. Drew? Yeah, do the Monte Carlo integration on G. Pick a bunch of uniform samples on 0, 1, and compute G of x as we did in the first problem. And compute integral of G of x as we did in the first problem. So method one says to apply the method, the first problem technique. That is to say, pick x1, x2, uniform IID 0, 1, and do Monte Carlo to compute g of x dx. Integral from 0 to 1, g of x dx, which is EP of f, etc. That's what you do. Okay? And what is the variance? What is the var z in that for that method? So if we do this, then what is our variance of estimate? So if I let z equal g of x, f of x, and choose the x's ID uniform, then the variance of z, which is the numerator of the thing that determines the convergence rate, the formula is right up there. It's the integral from 0 to 1, g squared of x dx, minus the integral from 0 to 1, g of x dx quantity squared. And if I plug in what the g is, that's the integral from 0 to 1 of f of x squared, p of x squared dx, minus EP of f, the quantity squared.
after the IID?
Yes, IID hyphen interval 0, 1. Yeah. Okay, method 2. And remember, this whole discussion of the Monte Carlo integration was predicated on the fact that computers were very good at picking uniform on 0, 1 random variables. What if we could use a computer to pick a bunch of samples distributed according to p? That is to say, you're going to have a lot of samples where p puts a lot of weight, not many samples where p puts a little weight, and have the computer able to do that. Okay, so suppose that by whatever means necessary, Malcolm X type thing. Okay, so suppose, I'm not going to tell you how to do this yet, so we'll see soon how to do this, but just bear with me for now. This is where we put Markov chains to work. Suppose that instead we could pick, say, y1 through y2, y3, and so on, IID distributed according to p. Not uniform, but according to this p that we started with. Right? Suppose we could do that. Then let z, the z sequence, be given by just the f of the y's. So z1 is f of y1, z2 equals f of y2, etc. Okay? Then what's going to happen? By strong law of large numbers, if I take 1 over n times the sum from m equals 1, or what is their common mean first? What is the common mean of all these z's? The z's have common expected value. What? Integral from 0 to 1 of f of y p of y dy, which is just EP of f. So they have the same common mean. They have the thing we want to compute. Okay? And they are IID. By the strong law of large numbers, when you catch me looking over my shoulder at the clock, you know I'm probably trying to tell you too much in too little time, but let's just try it. By the strong law of large numbers, 1 over n times the sum from m equals 1 to n of these z's, which is just 1 over m, n times the sum from m equals 1 to n of f of the y's, converges as n goes to infinity with probability 1 to EP of f. Okay, which is what we want to compute. What is the variance of the z's here? Let's figure that out and compare it to the variance of the z's in method 1. So for this method, the variance of the z is equal to the variance of f of y. Okay, so that's going to be the integral from 0 to 1 of f squared. First I'll write it's going to be e of f of y squared minus e of f of y, all that squared. E of f of y squared is going to be integral from 0 to 1, f squared of y, p of y dy. And this is going to be EP of f, again, squared. Let's compare this with the variance from method 1. There's only one tiny difference, but it turns out to be huge. They both have as trailing term EP of f squared. But the first method has f squared p squared. The second method has just f squared p with an o squared. It's up here. I saw you looking over into the, Asia. So let's compare. Thus, the variance of z from method 1 minus the variance of z from method 2 equals the integral from 0 to 1 of f squared p squared. And I'm just going to turn the y's into x's because it's just a dummy variable of integration. So minus f squared of x, just p with no squared, all that dx. And you can factor an f squared out of this, or an f squared p. What do I want to factor out of that? I knew I was trying to cram too much in. Well, anyway, that's what it is. Let's pick it up from there next time, because it turns out that if p is very spiky, right, then method 1 is going to have a much higher variance than method 2. Okay, and to drive that point home and why it's important, I need more time. So I'm just going to drop it there, and we'll pick it up.